So this sine area of this oriented triangle is equal to the cross product of this vector with this vector. So we just express it in terms of the points themselves. The sine area of the oriented triangle OAB is 1/2 of OA cross OB. So the natural question is, could we use this to define the sine area of a more general oriented triangle, say ABC? ABC somewhere in the plane, not necessarily connected to the origin. And the answer is happily yes. Now, in order to get at the sine area of a general triangle, we need a preliminary fact first. That's given by this triangle cross product theorem, which says that for any oriented triangle ABC, say like this one here, is an oriented triangle ABC, you see that the orientation is specified by the circle inside with the arrow, meaning that we're going in this direction. There's a circular aspect to these three things. Even though we read it ABC, it's really the order, cyclical order that matters, the order that's going in this direction, as opposed to going the other direction. Okay, so for any oriented triangle such as that, ABC, the following three cross products are all equal. AB cross AC equals BC cross BA equals CA cross CB. How can you remember that? So think about the cyclic ordering here. The first cross product is AB times AC. So we're starting at a vertex, and the first vector that we're considering is the one that goes from that vertex to the next vertex. And then the other one is the one that goes from the first vertex to the one following the next one. So start at A, then we get AB first, and then AC second. Now if we rotate by 1 and go to B as a starting point, we're still going in that direction, then the first vector is BC, and then the second vector will be BA. So we have BC cross BA. And if we go to the third point, C, then the first vector, if we're still going in that same order, would be CA, and then CB. Okay, so there's nothing really confusing about this, as long as you remember that there's a cyclical ordering here. We're going from here to here to here. So it's the relative cyclical order that's crucial. Okay, so let's prove this. We're going to prove it by setting up some vectors and using the vector linear algebraic properties of the cross product. So let's set the vector AB to be U. Let's call that U. And the vector AC will be V. Then the third vector that we're going to be using is the vector, say, BC, going from B to C. And that's going to be V minus U. Let's just check to make sure that we believe that. So this is V minus U. You can see that if you start here and you take U and then you add V minus U, that combination is the same as just V. That's why this vector is V minus U. So when you add it to U, you just get V. Another way of remembering this is that to go from the head of one vector to the head of another vector, as in BC, you take the difference of the final vector minus the initial vector. Okay, so now let's have a look at BC cross BA. In terms of U and V, what are these things? Well, BC we've said is V minus U. And what is BA? Well, AB is the vector U, so BA would be the vector minus U. All right, now by the distributive property of the cross product, this is going to be V cross minus U plus minus U cross minus U. And I've sort of taken both of those minus signs out. So there's a minus U cross minus U actually here, but the minus sign comes out front, and then the other minus sign comes out front, and they both multiply to give us just a plus sign. All right. So we get V cross minus U plus U cross U. But this minus sign can come out front by the linear property, so we get minus V cross U, and the U cross U is 0. That's the skew symmetric property of the cross product. Now, minus V cross U is the same as U cross V. That's, again, a skew symmetric property. And by that time, we see that we're back to AB cross AC. So we've been able to manipulate things to convince ourselves that BC cross BA is indeed the same as AB cross AC. And now let's check the same thing for this third cross product, CA cross CB. What is CA? CA. Well, that's going to be minus V. And what is CB? Well, it's the negative of BC, so it's going to be U minus V. Sorry, from C to B is going to be the negative of this one, U minus V. And then the linear property of the cross product, again, gives us, this is minus V cross U, that's the first term. And then there will be plus minus V cross minus V. And for the similar reason as up here, the two minus signs combine to give us a plus sign. And in any case, this thing is 0, and so the next line is just minus V cross U, where again, the minus sign has been taken out by the linear property. Again, minus V cross U is the same as U cross V, and we see that we're back to AB cross AC. So yes, indeed, each of these other cross products are the same as the original one. So let's have a look at the diagram. What is this actually telling us? Well, it's telling us that AB cross AC is the same as BC cross BA is the same as CA cross CB. In each case, the first vector is in the direction of the next one in the order, and the second vector is the vector in the direction of the previous one in the order. So it's nicely cyclically symmetric. And that's really great. That means that when we have a triangle like this, if we want to compute one of the cross products, we can replace it with any of the other two cross products as long as we go in the cyclical orientation that the orientation dictates. So it gives us a flexibility in terms of defining and calculating cross products. All right, great. So now here is sort of the main definition. For an oriented triangle ABC, its sine area is S of ABC equals 1/2 AB cross AC. But it also equals 1/2 BC cross BA. It also equals 1/2 CA cross CB. We've just seen in the previous theorem that all of these quantities are the same. So their common value is going to be the sine area of the oriented triangle. So we don't insist that we have to choose one particular vertex because we really want to think of these three vertices as all being sort of on an equal basis. So it's 1 half of AB cross AC, or it's 1 half of BC cross BA, or 1 half of CA cross CB. So, for example, here is a oriented triangle ABC. A is the point 3,1, B is the point 4,3, C is the point 1,2. Then, the sine area of ABC is what? Well, we can use any one of these three to make the calculation. The previous theorem tells us we're going to get the same answer whichever one we use. So let's use the first one, say AB cross AC. AB cross AC. We have to find those two vectors, which are relative positions, and then take their cross product. So what's the vector AB? Well, it's going to be the difference in the coordinates here. So final minus initial. 4 minus 3 is 1. 3 minus 1 is 2. So this is the vector AB. It's the vector 1, 2. And what about the vector AC? Well, again, final minus initial. 1 minus 3 is minus 2. 2 minus 1 is 1. So there's the vector AC. So this is AB cross AC, and we have to take half of that. And when we use the cross product, well, it's an AD minus BC kind of thing. So we have 1 half of 1 times 1 minus 2 times minus 2. For a grand total of 5 over 2. And I'll let you check that you get the same number if you start with the vertex B or the vertex C also, and consider just the vectors emanating from either of those. This is great. So now we have a definition of the signed area of an arbitrary oriented triangle. So we've just defined the signed area of an oriented triangle. That's great. But now we're going to do something in addition to that, something which is maybe a little bit curious, something that maybe you don't see in a typical calculus course. We are going to define the signed area of an actual oriented side, of just a segment which is oriented. So here's the definition. For an oriented side AB, its signed area is S of AB. And by definition, that's S of OAB, the oriented triangle OAB, where O is, of course, the origin. And we've just seen that that can be expressed in terms of a cross product if we want as 1 half of OA cross OB. So here is a point A, here's a point B. Here is the segment AB, or the oriented side AB. Actually, officially, an oriented side is just a list or an ordered set of the 2 points, A, comma, B. That's officially what it is. But we write it down pictorially in terms of the segment with that arrow in the middle of it. Okay, that is the oriented side AB. It's like a line segment, but it has a direction, a start and an end. Okay, we are now going to find the signed area of this segment. And the definition is, it's the signed area of OAB. This oriented triangle, O is the origin. That's an oriented triangle, has a signed area. The signed area is 1 half of the vector A cross the vector B. So, just in terms of the vector little a and the vector little b, which are the coordinate vectors of the points A and B, in other words, the vectors emanating from the origin to the point A and to the point B, then we can write just S of AB is 1 half of A cross B. And let's note that if we interchange the orientation of the oriented side, S of BA, that's going to be minus S of AB, because that would just amount to interchanging the order of the two vectors in the cross product, which would just introduce a minus sign. So this is an intriguing kind of thing that we're doing here, maybe not obvious, why we would want to introduce the signed area of actually a side. And it sort of has to do with the position of the origin. So if the side is far away, then maybe the triangle has a relatively bigger area. If the side is closer, then maybe it has a relatively small area. So it's not just a question of the shape of the side, it's also where it is that's going to impact on the signed area of that side. So the importance of that notion becomes clear with this following theorem. The triangle signed area theorem. It is that for any oriented triangle ABC, the signed area of ABC, S of ABC, is equal to S of AB plus S of BC plus S of CA. The signed area of the oriented triangle, ABC, which is sort of represented by that red area, is actually the sum of 3 signed areas of its 3 oriented sides. So AB there would give us a triangle OAB. So this first thing here really corresponds to the signed area of that triangle there. And this one here, S of BC, corresponds to the signed area of the triangle BCO. So that's that triangle there. And this third one, S of CA, corresponds to the oriented triangle CAO. Okay, so that's that oriented triangle there. So the geometrical content is that if you want to calculate this area here, the signed area of ABC, that oriented triangle, then you can do it by taking the area here, OAB, adding the area OBC, and then the area of OCA. And what happens here is that the orientation of these 3 triangles, determined by the 3 oriented sides, has some cancellation. That this oriented triangle here, the OCA one, that area will end up canceling with the contribution of the areas from the original ones in these portions here. So we end up getting this big area plus this big area, essentially sort of minus this big area in terms of absolute values. But that's not really the best way to think about it, just a signed area concept. It doesn't matter which ones are positive and which ones are negative. Okay, so let's prove this. And we'll do that by introducing coordinate vectors for our 3 points, A, B, and C. So let's let OA be the vector A, OB be the vector little b, and OC be the vector little c. Okay, so then what is the signed area of ABC, which is on the left-hand side here? Well, by definition, it's 1/2 of AB cross AC. And what is AB? It's the vector from here to here. And in terms of this vector A and this vector B, it's B minus A. That's what AB is. Cross AC, here's AC. From here to here, in terms of the vectors A and C, this is vector C minus vector A, C minus A. Okay, now we're going to use the distributive property of the linear aspect of the cross product. In this calculation here, there's really 4 terms. There's a B cross C, there's a minus B cross A, there's a minus A cross C, and there's a plus A cross A. And we know by now that an A cross A is going to be 0, so there's no need even to write that down. And now we're going to rearrange things because the minus B cross A can be rewritten as A cross B. We interchange the order, we introduce a minus sign. And the minus A cross C can be written as C cross A. So these 3 things become A cross B plus B cross C plus C cross A. And that's exactly what's appearing on the right-hand side here. 1/2 of A cross B is S of AB, 1/2 of B cross C is S of BC, and 1/2 of C cross A is S of CA. So proof of the triangle sine area theorem that allows us to rethink the area of a oriented triangle ABC in terms of the sine areas of the 3 oriented sides, AB, BC, and CA. This technology is actually very useful. It's very useful to be able to calculate the area of a triangle from knowing its 3 coordinate points. So let's have a look at an example. Here's a triangle ABC. A is the point 2, 1, B is the point 1, 4, C is the point 3, 3. And we're interested in the area of that triangle. Let's actually color it so we can see what we're talking about. So that's the triangle that we're interested in. And we have oriented the triangle ABC. So we want the sine area of that oriented triangle. Okay, so what's the definition of S of ABC? Well, it's 1/2 of AB cross AC. AB cross AC. So we take A to the next one in the order, cross A to the previous one in the order. All right, what are these vectors between the points? Between the points A and B, we have to take a difference in coordinates. Okay, so this is a 1 minus 2, that's a minus 1, and 4 minus 1 is 3. That's the vector AB. And what's about the vector AC? We have to take a difference between these 2 coordinate points. 3 minus 2 is 1, and 3 minus 1 is 2. So the formula for the sine area is take the cross product of these 2 vectors. That's minus 1 times 2, minus 3 times 1, so that's minus 5. We have to divide by 2. We get minus 5 over 2. Great. Okay, that's cool. But now let's illustrate how it would work if we looked at the other side of the previous theorem. Let's look at the sine areas of the 3 oriented sides. Let's look at AB first. Okay. So with AB, the oriented triangle OAB, we calculated sine area just by taking the cross product of the vector here times the vector there divided by 2. So those vectors are just the coordinate vectors associated to the points A and B. So this vector here emanating from the origin to A will just be the vector 2, 1. And the vector OB will be 1, 4. So the oriented side AB has sine area 1/2 of 2, 1 cross 1, 4. And then 2 times 4 minus 1 times 1, that's a 7. 7 over 2 altogether. So that's the sine area of the oriented side AB. And what about the oriented side BC? Well, then we have to take the vectors B and C here. So basically the coordinate vectors of these things, which is 1, 4, 3, 3. Okay, the cross product there is 1 times 3 minus 3 times 4, that's minus 9 all over 2. And finally, CA, we have to take these points and their associated coordinate vectors, 3, 3, cross 2, 1, and that's equal to the cross product 3 times 1 minus 3 times 2, that's minus 3 divided by 2. So you can see that we're doing something a little bit different than we were doing here. Here we had to find differences between points. Okay? Here we're just relying on the actual coordinates themselves, but admittedly we have to do more work, do 3 of them. Okay, when we add up all of these sine areas of the oriented sides, what do we get? We get 7/2 for S of AB, minus 9 over 2 for S of BC, minus 3 over 2 for S of CA, and that totals minus 5 over 2. So we do get the same answer as in the original calculation. So that triangle sine area theorem that we just talked about has an immediate consequence of a famous formula that's usually associated to linear algebra. It's a formula for the area, or like the sine area of a triangle, in terms of actually the coordinate points. So suppose that we have a triangle. Now we'll change notation a little bit. We'll call it A1, A2, A3, and the points will be general points. So A1 is X1, Y1, A2 is X2, Y2, and A3 is X3, Y3. And we're interested in the sine area of the oriented triangle A1, A2, A3. Okay, here's the formula. Its numerator is a little bit complicated. It has these 6 terms. X1, Y2 minus Y1, X2. Well, that's just the cross product of the associated vectors here. X1, Y2 minus Y1, X2. And then the next the special case when we actually know what the 3 points are. And these ingredients here are just the various assigned areas of the oriented sides of the triangle. So the natural question is, can we now extend this notion of sine areas to more general figures? For example, to quadrilaterals, or maybe to more general-oriented n-gons. Here is a quadrilateral, 4 points, A1, A2, A3, A4, and there's a specific order that we're going in, going around this direction here, so it becomes oriented in the same way that an oriented triangle is oriented. And it's represented by this little circle here that sort of represents the orientation, and that's obvious terminology that we could use to represent such an oriented quadrilateral. And the natural question is, can we have a theory of sine areas for these things? Can we get sort of corresponding formulas? So let's investigate this question about how we should approach the idea of a sine area of an oriented four-gon, let's say. This one here, A1, A2, A3, A4. And an obvious thing to do is to say, well, why don't we decompose this into triangles, because we know the sine areas for triangles. So let's pick some point B, in this case, in the interior of this quadrilateral. And then we see that by joining B to the 4 points, we get 4 triangles. And the orientation that we're assuming on the original quadrilateral, A1, A2, A3, A4, automatically induces orientations on each of these subtriangles. Okay? Because implicit in this orientation is the fact that this side is oriented this way. I mean, this side is oriented this way, then that's consistent with an orientation in this direction of this triangle. Similarly, the orientation of this side gives an orientation of this triangle like this. The orientation here gives us an orientation like this. And the orientation here gives us an orientation like this. So each of these subtriangles is actually a oriented triangle, which is good because then you can think of sine area. So a logical progression would be that if the sine area of the quadrangle is defined, it ought to have the following formula. It ought to be that the sine area is the sum of the sine areas of the 4 constituent triangles, namely A1, A2B, and A2, A3B, and A3, A4B, and A4, A1B. Okay, so let's investigate what that would mean. Because we know that each one of these oriented triangles can be further reduced into a sum of 3 oriented sides, or sine areas of oriented sides. So for example, A1, A2B, this triangle here, A1, A2B, its sine area is actually the sum of the 3 sine areas of its oriented sides, namely S of A1, A2, S of A2B, and S of B, A1. Similarly, the next one, A2, A3B, is a sum of its 3 signed areas of oriented sides, namely S of A2, A3, plus S of A3B, plus S of B, A2. And then the next one, which is S of A3, A4B, there it is there, it's the sum of this one. And when it's pinning down what this quantity actually is, we can then define this thing in terms of the sum of these 4 signed areas of its oriented sides. Okay, very important that we're first proceeding by thinking about what the definition of the sine area of the region in question is. Not assuming that we know that. We have to pin down what that sine area is, and here we have pinned down a very good potential choice for what the definition of the sine area of a quadrilateral might be. Okay, so that analysis leads us to the following definition. It's a definition of the sine area of an oriented four-gon. Four-gon A1, A2, A3, A4, it's an oriented four-gon, or quadrilateral. And the definition is that the sine area is going to be, just as we said, the sum of the sine areas of its 4 oriented sides. S of A1, A2, plus S of A2, A3, plus S of A3, A4, plus S of A4, A1, closing the circle and coming back to where we started. So A1, A2, A3, A4, in this case, orientation in this direction, fine. Then we have these 4 oriented sides, and they are there. Then if we include the origin here, then we have these 4 oriented triangles, each one corresponding to a side, as well as this one here. But this one here will actually have this orientation. And when we add up the sine area of this, plus the sine area of this, plus the sine area of this, plus the sine area of this, then we get what a reasonable notion for the sine area of the quadrilateral. And so now we can rewrite that in terms of Meister's formula. So Meister was really the first person, I think, to understand this approach to signed areas of triangles and n-gons. And so this is a formula that he wrote in a paper around 1769. And so in the case of the quadrilateral, here we can state it in this way. That if we have 4 points, A1, which is x1, y1, A2, which is x2, y2, A3, which is x3, y3, and A4, which is x4, y4, then the sine area of the oriented quadrilateral A1, A2, A3, A4 is given by this expression here. It's 1/2 of x1, y2 minus y1, x2 y2 plus x2y3 minus y2x3 plus x3y4 minus y3x4 plus x4y1 minus y4x1. And each one of these rows is just one of these terms. So this is just s of a1a2, this is s of a2a3, this is s of a3a4, and this is s of a4a1. With half, of course. So it's a beautiful extension of the triangle formula. So if we just have 3 points, then the triangle formula that we wrote downwards is just analogous to this, but we just go A1, A2, A3, and then back to A1. And the beauty of this formula is that once you understand it, you can see that it's automatic how to generalize it to more than 4 points. Right? We can now talk about the signed area of an arbitrary oriented n-gon. And it's exactly the same story. We just cycle through the various oriented sides, starting from the first, going to the end, and then coming back to the first one. So we covered a lot of material today, done a lot of interesting things. We've really established a good framework for understanding area, the subtlety of area, in particular signed area in the plane. It's crucial that we work with signed area. And we're going to see a lot more examples of the power of this thinking, both in the course materials that are associated with this lecture, okay, which I hope you're all going through,